Hello everyone, thanks for joining in today. Let's wait just a few more seconds for maybe some more people to join, and then the plan is to show you some vintage equipment that I have around here, and I want to do some experiments with them as well. Okay, so I'm I said in the chat what I'm about to do so that we are on the same page. Let's see if more people gather around here, and if you're watching and everything's okay and the audio is good, maybe say a hello or something in the chat to make sure that everything's working. Okay, so first of all, I think it would be interesting to do a small tour of the equipment that I have at hand for today's experiment. So let's start with that. I will take the phone off the stand. First of all, I have this digital Siglent oscilloscope. This will come in handy for some of the experiments today. We also have signal generator for generating some test signals for our experiments. We have a really fast pulsar designed by Jim Williams and redesigned by my friend from Gears and Gear, who also runs a nice YouTube channel. This creates some really fast pulses that are good for testing oscilloscopes up to their limits most of the time. Then we have this Tektronix 515A oscilloscope. It's all vacuum tube except for some diodes. It's missing the panel so you can see what's inside. We can play with this as well. Let me give you a quick tour. And then we can use this one as well. This is a Tektronix 466. This one's a little bit more interesting maybe than the classic 465 because it has analog storage, so this is a pretty wild feature. So yeah, maybe we'll play with this as well. Okay, so in the first part of this live, I would like to explain what an oscilloscope is and how you can use it and what it can do for you. Let's see if that's interesting for anyone around here. So if it is, please let me know in the chat. And also let me know how familiar you are with oscilloscopes. This would really help so that I know how to present the whole thing. Meanwhile, I will put the phone back on its stand. Okay. So an oscilloscope is used for visualizing signals with respect to time. This is a really important thing to mention because in electronics we have lots of other types of graphs which are not necessarily graphs with respect to time. For example, if we look at a spectrum analyzer, the graph that we see on the screen is amplitude versus frequency, so that's something else. Then we have curve tracers, which are really common as well, which display current versus voltage, and we have oscilloscopes which display voltage versus time most of the time, except if you have a current probe, of course, when you will see current with respect to time. In most cases, you are probably looking at voltage. So let's see how we can plot a function with respect to time, maybe even without using an oscilloscope, using just pen and paper. So to do this, let me readjust things around here. Well, the easiest thing that you can do is you can have, let's say we want to plot the movement of this hand with respect to time. Let's imagine this is our signal of interest or something like this. Well, the simplest thing that we can do, and this was actually done in the past, maybe still done in some weird context, I don't know, is to have it plotted on paper. So as my hand moves, uh, we can simply move the paper at constant speed from left to right, and then we get a plot. So there are devices that do this. For example, the ones that monitor earthquakes or all sorts of industrial things that that maybe have to monitor something long term. In that cases, it makes sense, or let's talk in the past. I think it made sense at some point to have them plot some functions on paper. Hello Andy, thanks for joining in. So let's see how this translates into what an oscilloscope does. Well, let's move our focus to the Tektronix 466 in this case. Well, first of all, an old scope like this one is based on a CRT or cathode ray tube. So let's see what a cathode ray tube can do for us. Well, the most basic thing that it can do is actually a dot. Let's see if we can get a dot here. Are we out of the screen or what? Okay, and here it is. So the most basic thing that it can do is a dot like this one, and after applying the proper focus voltage on its focused electrode, we can focus this dot into a really tight beam, just like this. And now this is useful for plotting things on the screen. So what the cathode ray tube does is that in the back of the device, in the back of the scope actually, we have what we call an electron gun that, as the name implies, shoots electrons towards the phosphor screen that we can see right here. The electrons are accelerated by a really high voltage, and the interaction between the electrons and the phosphor screen creates visible light, which is what we see right here. In order to focus the electrons into this tight beam that we can see here, we have some electrodes inside the tube that look just like some metallic rings or something like that, and those electrodes are basically the electrostatic equivalent of lenses. So we have to focus the beam into a tiny dot, just like we would do, let's say, with magnifying glass or something like that, by adjusting it, by adjusting the distance between the magnifying glass and the screen. As soon as the distance between the magnifying glass and the screen is equal to the focal length, then we get a really tiny dot of light, and this is exactly what happens here, but this happens with electrons instead of light. So not only can we focus the electrons in a really tight dot, but we can do something else. And what we can do is we can have vertical control over the beam and horizontal control. This is achieved using some deflection plates which are inside the tube that can deflect the beam left or right and up or down. Let's demonstrate this really quickly. So, for example, we can adjust this, and this is our vertical axis. Obviously we have control on the vertical axis, and then by changing the voltage on the other two plates, we have control over the horizontal axis as well. So now that we have this, we are one step closer to plotting something with respect to time. Let's see how we can do that. Well, it would be nice if we had a DC source at hand. But this is, let's see, a DC source is pretty far away from the scope at this point. So yeah, what happens here is that you can apply a voltage at the input of the scope, and as the voltage goes up, the dot goes up, just like so. As the voltage goes down, the dot goes down. So this is the first step to plotting something with respect to time. We have to adjust the dot on the vertical axis with respect to the input signal. The next step is to move the dot on the horizontal axis, just like we did with our sticky note, in order to get a graph like this one. And of course we can do this manually if you want to, but that's not the point, and that's not how we use the oscilloscope. So yeah, what we do is we use a section of the oscilloscope to create left to right motion at constant velocity. Well, first of all, let's imagine we don't have this sort of functionality, and let's imagine we only have manual control over all this. So in order to see the plot, what we can do is we can enable analog storage, and we can repeat the experiment we did on paper using the oscilloscope. Let's try this. Okay, so let's imagine this is our input signal that we are trying to plot. All that we need to do now is to move the dot at constant speed from left to right, and then we should get a plot. And it is right here, it's slowly fading away. This is basically what the oscilloscope does. Now, of course, as I said, the scope does the motion from left to right automatically, so by slightly adjusting the settings here, the dot can move from left to right on itself. So let's do that. In order to do this, we have to enable the time base. And here it is. Now it's moving on its own. It's slightly off screen, so let's adjust the horizontal position. And after a few adjustments, we should have some motion from left to right that covers the entire screen of the scope. And we do. At this point, it looks really nice, I would say. So now that this is all set up, let's repeat our experiment once again, trying to achieve something that we managed to achieve on paper. So now all that we need to do is to apply our signal at the input. This will deflect the dot, and this will plot the signal with respect to time, just like so. As you can see, it can go really fast, it can go really slow, and using the proper settings we can accommodate for all that and display the signal properly, let's say regardless of its speed, even though it's really fast or really slow. That's why we have so many adjustments here. So now that this works, let's take things a step further by applying a test signal. For this I will use my signal generator to generate a sine wave, a really slow one that just fits our purpose of watching things go really slowly. So let's go to waveform, sine wave. Let's set the frequency to some really low value, let's say 1 Hertz, something like that. Okay. Then we have to connect this to one of the inputs. So here's the output from the signal generator. This needs to go back to the scope on the channel that controls the vertical axis, of course, which is this one, I guess. Okay, let's enable it and see what we get. Nothing, because we forgot to enable it. Let's turn it on, and now we get our beautiful sine wave. So I hope you like this demo, because I think it's really beautiful, because with this particular scope being analog and having analog storage, you can actually see what's going on by slowing down the oscilloscope a lot. Hello Andrea, hello Gabriel. This is I would like this live stream to be in English, because it's on the international channel, so just to be on the same page, and for the international viewers to understand the chat and the explanation here, I would like everything to be in English, if that's okay for everyone. Thanks. I will do live streams in Romanian as well. I usually do that on TikTok, but this will happen on YouTube soon, in the near future, because I want to experiment with it, and I want to see what sort of audience I have on YouTube as well. Oh, so you're based in Italy, nice. Hello from Bucharest. Let's take a quick break here. I want to invite some more people onto the live stream, and then we will move on. Just give me 1 second, please. Okay, so let's move on. By now, I hope you get an idea of what a scope does. Yes, I'm from Bucharest, by the way. I've just moved to Bucharest, actually, from a different city in Romania. Anyway, so I hope you have by now, let's say, at least a shallow understanding of what an oscilloscope can do. That's why I'm running this crazy slow. So remember what we did on paper. This one is doing pretty much the same thing, but everything is electrostatic. So yeah, now that this is set up, let's take things a step further by speeding everything up. So let's disable storage. As you can see, without the analog storage, it doesn't look all that great because we don't have the persistence anymore. So it's hard to tell when it's moving so slow that we get actually that we have exactly the same thing. So let's use it how you would use most of the scopes, which is a lot faster than this setting right here. That's why we have the time base. So let's make things a lot faster. Okay, and now that it's a lot faster, we no longer have a sine wave here. So let's do something about this. Now what we can do, since it's running a lot faster, is to make the input signal a lot faster. So let's readjust the signal generator and go to like 100 kilohertz or something like that. Maybe this will start to showcase what an oscilloscope can do and how fast it can go. And actually this is still crazy slow for an oscilloscope, because the high-end ones go up into gigahertz, tens of gigahertz maybe for the fastest ones, even though I don't have something like that. This one, I forgot the bandwidth of this one, but I think it's like 100 megahertz, 50 megahertz or something. Yes, that's right. The left scope is all tubes. I've showed this. I've shown this at the beginning of this live stream, and I want to play with it in this live to just a little bit later. Let's. I would like to continue the explanation of what the scope does, and then at some point I want to play with the vacuum tube one, of course, because I love vintage gear, as you can see. So yeah, now that our input signal is faster, we can actually get the sine wave once again. So finally we have a sine wave on the display. once again similar to what we did on paper, but now the scope is doing exactly the same thing, but it's doing it so fast that we no longer see the left to right motion. That's why in the beginning I wanted this explanation to be really slow, so that you get a feeling of what's going on here. But when you operate an oscilloscope, most of the time it's so fast that you cannot see the motion from left to right. So here, due to the persistence of the phosphor screen, it looks like a continuous graph. And of course, the persistence of the human eye comes into play as well, especially at relatively low frequencies. So in the end it looks like a continuous graph, even though strictly speaking it's not. It's exactly what I've shown before, just a lot faster. So yeah, let me know if the explanation makes sense up to this point, before moving on to some more detail about how to adjust everything that we have here actually. So please let me know in the chat if things make sense up to this point before moving on to something that's a little bit more advanced, let's say. This explanation, since you're watching this, maybe most of the things were something that you already knew, but just to be on the same page, I wanted to start with the basics. So now that we've talked about this, I think we can move on to something else, which is talking about all these adjustments that we have on the front panel. Because as you can see, we have lots of adjustments, and what I noticed, especially when I was studying electronics at the university, is that these sort of adjustments create lots of confusion, maybe because they're not explained properly whenever you're trained to working with something like this. So I want to compensate for that, and I want to show you what all of these adjustments do. Let's move a little bit closer to this. Okay, so let me know in the chat if you're familiar with all these settings, or if you would like to get some more info about how to adjust everything. I'm really curious to know how familiar you are with the oscilloscope, and I would love to have some interaction here so that it doesn't become too boring, or it doesn't become like a monologue. Okay, so what you need to know about the settings that you find on an oscilloscope, no matter if it's an analog or a digital oscilloscope, is that the oscilloscope can be split into some discrete sections, let's say, discrete sections that we can adjust individually. And if you do that, all of a sudden the thing starts to make sense and starts to become less overwhelming. So yeah, it's a 466. This one, it's a little bit more interesting than the 465, I would say, because it has analog storage, which is wild in my opinion. And I love this sort of vintage stuff for explaining what an oscilloscope does, because it can run crazy slow and you can actually see what's going on and how it's plotting something on the screen. I think it's really nice, but of course we can move on to a digital one just a little bit later. And I would, even though I have to say that the settings and how you adjust it applied to digital scopes as well. It's just that we have some extra stuff on the digital scope and far more convenience usually in terms of amplitude measurements, frequency measurements, and so on. But yeah, you have a hint right here that this scope can do some measurements, so that's why it has a 7 segment display on top. And maybe I'll demonstrate that as well because it's really nice. So Gabriel here says that he would like to use it for audio gear and for debugging. Well, yeah, the scope is great for that, and fortunately, since audio is really low frequency, almost any scope will do. And what I'm showing today would be really helpful for troubleshooting audio stuff, I'm sure. Okay, so as I said earlier, here we have like 3 sections of the oscilloscope that we need to adjust independently. What we have to the left side of the front panel is what we call the vertical section. And of course, as the name suggests, this controls the vertical axis of the display. And the vertical axis is the one that's driven by the input signal. So as you can see, with the signal out, we get no vertical deflection and we only have a straight line, which demonstrates that the vertical is driven by the input signal. So what the vertical can do is, first of all, let's look at the input coupling. This is really important. A scope like this has 3 modes for input coupling. It has ground, which means that the signal is basically disconnected from the vertical section. Then we have DC, which means that the signal is directly connected to the vertical section. And then we have AC coupling, which means that the input signal is connected to the vertical section using a blocking capacitor that basically removes the DC component of the signal. So let's demonstrate that actually, because things make more sense when you see them in practice, I think. So let's go to DC coupling and let's apply an offset to our signal from the signal generator. So right now the offset is 0. I will move you to the signal generator really quick. The offset is 0. Let's set 50 millivolt, 500 millivolt offset or something like that. And let's go back to the scope to see what happened. Well, now with the offset, our signal is out of screen. It was shifted up, as you can see, due to the offset. Let's see if we can get rid of it. Well, we can. We can simply use AC coupling, and the DC blocking capacitor inside the oscilloscope gets rid of the DC component, and now the offset doesn't matter anymore. So in some cases you want to use AC coupling, and in some cases you want to use DC coupling, and there are no hard rules here. It all depends on what you're trying to see. For example, let's say when debugging an amplifier, most of the time you would probably want to have DC coupling so that you will be aware of the DC offset of certain signals, because this can indicate faults in some cases. By understanding how a schematic works, you can probably guess what signals need to have an offset and what don't. So I think it's useful to see that, at least initially. And then if you measure the offset with a multimeter and decide that it's okay, maybe you can get rid of it and go to AC coupling, and that's it. On the other hand, most of the time when you're debugging a power supply and you're only interested in ripple or noise or any sort of garbage that's going on the power supply, most of the time you don't care about the DC component and you only want to see the ripple. So that's where AC coupling comes in, because let's say you have a 10 volt power supply or something like that. you want to remove the 10-volt component, and then you can really zoom in on the garbage that's going on the supply line. So that's why this mode is for. Main Scientific here says something about an external storage scope. I'm not sure how that works. I'm not sure what external storage means. So it has some external storage unit. I don't know. That's interesting. In the case of this Tektronix scope, the storage is part of the CRT. This is not your typical scope CRT like the old vacuum tube one has. This is a special CRT that has storage. It's some sort of weird electrostatic storage that I cannot pretend that I understand how it works. It's at some point it's just beyond me. It's really interesting, but yeah, the physics behind are pretty wild, I guess. So yeah, let's go back to the vertical section. So far we've discussed coupling, and I hope this is clear for anyone, and you can see what's doing here because we have a signal that has an offset. Okay, and now there is another adjustment here that's really important, which is the vertical position, which is probably self-explanatory. This one just allows you to shift the signals up or down, and this would be useful in many cases. For example, if you have two traces, maybe you want some separation between them, so you want the channel 1 to be shifted upwards so that you have room for the other trace or something like that. Another use case would be, even for a single channel, if you want to measure the amplitude, especially on an analog scope, then you want to align the signal with the graticules so that you can measure the amplitude, and this is where the vertical position comes in handy. So what I usually do is that I try to get the peaks of the sine wave to match one of the horizontal lines, and then we can count how many divisions we have here and we can measure the amplitude. So that's why this setting is really important. And we have, don't really like this glare that we have on the screen. I'm sorry for this. It makes seeing the graticules a bit more difficult. That's annoying. Okay, so let's move on to the next important setting that we have here, which is the vertical sensitivity. So as I said, scopes are really versatile. They're supposed to display a wide range of signals. As somebody said in the chat, it can be used for audio stuff, but the scope can also be used for radio frequency stuff, and the frequency would be wildly different, so the scope needs to accommodate for that. And of course, even in the case of an audio amplifier or something like that, the amplitudes from one point to another would be wildly different. So if you're looking at a signal that comes straight from the microphone or the guitar or something, the amplitude will be relatively low, and maybe as you progress from one amplification stage to another, the amplitude would go higher and higher and higher. So to accommodate for all that, the scope cannot have fixed sensitivity, so the sensitivity is adjustable. As you can see, by turning the knob, the signal that we see on the screen gets larger or smaller, basically. This is really basic stuff. However, the nice thing about this is that the scopes are calibrated, and you can actually use them to measure the amplitude. So let's see how we can do that. For this, it would be ideal for this phone to be slightly higher. Okay, because this will help us see the vertical sensitivity setting. So for analog scopes, we usually have a rotary knob like this one, and the sensitivity is right here where the orange light is. Let me see if I can zoom in on that. Okay, so the vertical sensitivity is 0.2, as the Americans like to call it, meaning 0.2, and the unit is volts per division. Let's see what this means. Well, if we look at the screen, you will see that it is divided into squares. Let me reduce the ambient light here so we can see this better. Let me find where the glare comes from. Okay. Yeah, let me know if this is better. I'm trying to get rid of the glare so that you can see the reticules. So as you can see, the screen is divided into squares, which we call divisions. And since the scope is calibrated, we know exactly how much each division is. So whenever we are trying to measure amplitude, we look at the divisions on the vertical axis. And then for timing, like period, frequency, and so on, we use horizontal divisions. So in our case, since we're talking about the vertical section of the oscilloscope, we are interested in the vertical divisions. So let's see how we can measure the peak-to-peak amplitude of our signal. Well, we have a vertical sensitivity of 0.2 volts per division, and now we have to count our amplitude in divisions and multiply it by the sensitivity in volts per division. So let's see. We have 1, 2, 3, 4, 5. 5 divisions, which is peak to peak. So from this peak to the top peak, we have a total of 5 divisions, and we multiply that by 0.2, and we get 1 volts peak to peak. 1 volt peak to peak, which is exactly, of course, the setting that we have on the signal generator. They match really nicely, which means that the units are somewhat accurate. And the vertical section has some other settings as well. First of all, let's see, on Tektronix stuff we usually have a bandwidth limiter, and this limits the bandwidth to 20 megahertz. In some cases, if you have high frequency noise, maybe this would help. Then here we have a vertical mode selector, so we can do multiple things with the scope. We can look at channel 1, we can look at channel 2, which is just a straight line because there's nothing connected to it. And then we can have a look at both of them at the same time, and the scope has 2 different ways of doing the same thing here. And those 2 ways are displayed right here. So it says chop or alternate. Let's see what this means. Well, at high frequency they look like exactly the same thing, so guess what we're going to do? We are going to slow it way down once again, so that we can understand these 2 modes. Let's do that. Okay, so look what's going on here. We remember that we are trying to look at 2 channels at the same time, and this is a single trace oscilloscope or a single beam oscilloscope. So this is just basic CRT. There are CRTs that have multiple electron guns inside that can trace 2 completely different signals at the same time, but it's not the case here. So this means that the scope has to do some electronic tricks in order to get two traces on a single beam CRT. And as I said, it has two ways to do this. Right now, as you can see, the trace is rapidly alternating between one channel and the other. So whenever we have this vertical line, this is channel number one because it has a really fast sine wave at input. As you can see, we can turn it off and it disappears. And whenever we get a straight line, then the oscilloscope displays channel number 2. And this mode is called the alternate mode, which um, which you can see right here. It says alt out. So with the button out, it's on alternating mode. And of course, you can speed it up. And when it goes really fast, you don't notice that it's alternating between one and another, and you have the illusion of two traces when in fact you have a single trace. Okay, so we have another mode here which is called chop. Once again, at high speed it looks exactly the same, so let's slow it down and see what this mode does. Okay, here it is. So it's pretty strange because now it looks like we have two traces at the same time, but this oscilloscope is not really capable of that, so this is just a trick. So what happens here? Does anybody know in the chat what happens here? Let's see. Let's interact just a little bit before giving you the explanation. Come on, I want to hear your guesses before explaining what this does. Yes, so Mad Scientific got it right. In chop mode, it's jumping from one trace to another really fast. So fast that it looks like a single, like two completely different traces. But yeah, this is just an illusion, of course. It's jumping between them so fast that they look like two traces when in fact the CRT is not capable of two traces. But I think the signals are screwed up when the time base is really fast. Let's see. Actually, not really. It looks decent in this case, but yeah, in some cases, I think it would be beneficial to use alternate mode, and in some cases, especially if you're going really slow, then you need the chop mode, because otherwise, as you can see, you get bored until the other trace comes in. Not that you would use the scopes as slow as it is right now, so this is just for teaching purposes most of the time. The scope is rarely used this slow, but yeah, actually, nobody stops you from doing this, and especially on a scope that has analog storage, you can slow it down a lot and it's still a usable instrument. But I wouldn't say the same thing for the vacuum tube one, because this one doesn't have storage, but it can go crazy slow. But yeah, the explanation is a little bit different here. This one can go crazy slow, but it was supposed to work with a film camera, so I guess if you have a film camera here that takes a photo of the screen, then it makes sense because it will look like a nice photo. Yes, so Mad Scientific got it right once again. Sometimes with the right waveforms you can see the gaps between the traces, and sometimes you don't. So in this case I couldn't demonstrate the gaps, but they are there and they can show up at fast signals. Okay, let's see what else do we have here. The other ones are, yeah, they are visible, but I'm not sure what you were talking about. I thought you were talking about the chop mode, because when you're chopping, it's harder to demonstrate that there are gaps between them. It's hard to demonstrate that the trace actually jumps from one to another. In alternate mode, it's pretty easy, because you can put it in alternate mode and slow it down a lot, and you can see what happens. So yeah, for the chopping mode I wasn't able to demonstrate this, but you have to use your imagination. Okay, let's move on to the next settings that we have here. They are the next ones are pretty interesting, but they are pretty self-explanatory. We have a trig view, which enables you to see the trigger signal. So for that we need to talk about the trigger section, which is a completely different discussion, but at this point let's just say that we have an external trigger input that can trigger the time base, and this being Tektronix is of course as flexible as it can be, so it allows you to see the trigger signal here as a separate trace, which is really nice. Then you have add, which I think is self-explanatory. This just adds the two signals together, and you can display the sum of the two signals, and we can actually have fun with it in just a second, so that you can see what I'm talking about. And then we have invert. This simply inverts the channels. I'm not sure, I forgot how it works, if it inverts only the second channel or if it inverts both. I think it only works with the second one. Let's see, this is the bottom trace is the second channel. Yes, so I think it only inverts the second one. Yes, this one doesn't move. So you can invert it, and then you have a beam finder, which is an interesting feature. So this one is used especially if you screw up the settings and everything's out of screen. In theory, the beam finder should bring them back. They sort of do. See, now the traces are out, and yeah, if you do stupid things, you can bring it back, I guess, to see that it's still working. I don't know, pretty weird feature. I don't use it all that often, but it's there because it's a Tektronix and they thought of everything. Yeah, so let's hook it up to the signal generator using an extra BNC cable, so that we have something on both screens, and then on both traces, sorry. Then we can demonstrate how we can add signals and subtract them, maybe. Let's see. Okay, let's go back to the signal generator and change the settings to get two signals. So we are at 100 kilohertz. I think we can get rid of the offset. 1 volt peak to peak, and then let's go to the second channel and dial in the same frequency, 100 kilohertz, the same amplitude, 1 volt peak to peak. And you know what, let's generate the second one out of phase. So this one will have a phase of 180 degrees, and it should get signal that's perfectly out of phase with respect to the first one. Let's see if that works. Okay, with these settings we can move back to the scope and see what we get. Well, nothing, unless we properly configure the coupling. So let's go to DC, DC. You don't really see what happens here because the time base is too slow, so we can increase the speed. Okay, and now we get two nice sine waves that are out of phase from one another. So let's see. As you can see, they are perfectly out of phase. They are 180 degrees apart. And now we can enable the add functionality and see how their sum looks like. Are you ready for this? And we get a straight line, of course, because these are out of phase, so they just cancel each other. So this is where the basic math from school makes sense into a practical circuit. And I have to agree with Peter here that the quality of Tekscopes would never exist today. Far too repairable. So yeah, they are amazing. I really love them. And as you can see, they are really nice teaching aids, in my opinion. Because once you understand how a scope works using an analog one, I think you have a better feel of how to operate one and how to adjust one, even though you would normally work with a digital one most of the time. So let's change the settings just a bit and see what happens when we change the phase between the two signals. So any guesses here? What happens as we change the phase? Let me know in the chat, and after your predictions I will change the phase to see what happens. Yeah, so see, or you can go like Mad Scientific, who says that I still don't have a digital scope, so you can go fully analog if that's what you wish. I mean, I think it's yeah, it's pretty clear from today's demo as well that this is a perfectly usable scope, unless unless you don't do maybe digital stuff, or you don't want fast and convenient measurements for amplitude and frequency. But this one is certainly usable for audio stuff. I would argue that you don't really need much more than this. I actually use this for fixing guitar amplifiers. Yeah, so I see that nobody gave an answer in the chat, so let's do the practical demo anyway. Let's change the phase between the two signals and see what we get. Ready? Let's go to degrees. So now we are at 180. Let's go to 179. Can you see what's going on? If not, let's change the phase. Once again, let's go to 178, 177, 176. As you can see, now that they are not perfectly out of phase, the sum component looks like a sine wave as well. And if you do this mathematically on paper, you will probably get the same thing. So here's the thing in practice. And of course we can keep going. And as you can see, as they get more and more in phase, the sum component gets larger and larger. And I would say this is a beautiful practical demo of this concept from math. And let's go to all the way down to zero phase, zero offset between them. And that's it. Now they are perfectly in phase, and as you can see, the sum component is also a sine wave, and it has twice the amplitude of every single one. So I think this makes sense. And now, to demonstrate the invert functionality, we can invert this signal, and I guess we should get straight line once again. And we do. As you can see, if we invert the second channel, then the signals are once again out of phase, and their sum is 0, which gives us a straight line. So I hope this demonstrates what these functionalities do and how to adjust the vertical section of the oscilloscope. Let me know if you like this demo, and if you did, I will move on to the next section. By the way, if you want to know more about things like this, I would highly recommend you to study the manual of a really old school scope like this one, maybe even the vacuum tube one that we have here, the type 515A, because by looking at the schematic I think you can better understand how this thing operates. And not only that, but old school manuals usually have you know, a natural language, let's say, explanation of what the oscilloscope does. So it's not just the schematic, but you also have some text with an explanation. And with all this in mind, I think we can move on to the next section. Actually, one more side note before moving on to the next section. If you're wondering what's going on here, let's have a look at the maximum sensitivity that's available here. So if we go all the way up, it says 5 millivolts or 5 millivolts per division. So whenever you do this, the input goes straight into the vertical preamp of the oscilloscope. And as you decrease the sensitivity, what happens here is that the oscilloscope couples some attenuators between the input and the vertical preamp, and that's how you get multiple sensitivity steps in the vertical section. So the oscilloscope basically has a native sensitivity of 5 millivolts per division, and then you add in some attenuators to decrease the sensitivity, in case you were wondering how it does that. So that's basically what's going on here. Okay, and Peter says that, yeah, due to a faulty scope, he had to look at the schematic because he had no horizontal sweep. So yeah, usually you understand how these things operate when you try fixing one. So that's definitely my case, because I fixed this one, I fixed the vacuum tube one that's here on the table as well, and I also fixed some other ones. So once you have some issues with them and you have to figure them out, it really helps you understand how they work. Yeah, I forgot about the verniers. Thank you, Mad Scientific. So yeah, actually the vertical section also has a variable mode, so if you want you can adjust this continuously. Weirdly enough, the Siglent, which was made in like 2018 or something like that, doesn't have this functionality, but this ancient scope has it, and the vacuum tube one has it too. So this would be useful when measuring all sorts of things that need to be aligned on the vertical axis. For example, you can use the verniers to adjust the signal so that it spans between the 0% marking on the graticule all the way up to 100%, and this would be useful for measuring the rise time of certain signals. Strangely enough, I think modern scopes don't have it anymore. At least my Siglent doesn't. And yeah, you can do that on the horizontal axis as well, so you can play with the time base and adjust it continuously. And of course, this being Tektronix, it has a nice red light to tell you that you are in an uncalibrated mode. So once you do this, of course, you cannot rely on the vertical sensitivity anymore, because it's just some random number as soon as you take it out of the calibrated mode. This holds true for the horizontal section as well. So the uncalibrated light goes on, and then you don't know what your time per division is. Okay, with this in mind, I think we can move on to the next section, which is the horizontal section. So let me remind you that the horizontal section has to produce a constant movement of the beam from left to right. We can see that by slowing down the oscilloscope a lot. So this is what it has to do. Most of the time this has to be much faster than this in order for any sort of meaningful result, but fortunately we can slow things down for teaching purposes. So as you can see by now, this means that the horizontal section consists of some sort of oscillator, which we call a time base. What the time base does, especially in analog scopes, is that it produces a signal which is actually a sawtooth signal. So we have a constant ramp from a low value all the way up to a high value that produces this sweep, and once we reach the maximum value, which is the right side of the screen, the time base jumps back to zero, and after a wait time it produces a new sweep at constant speed. So this is what's going on, and the signal looks actually like a saw, so that's why it's called sawtooth waveform. It literally looks like saw teeth. So what we can do here is we can adjust the rate of this movement in order to accommodate for signals that are faster or slower. We can actually turn it off, and we can use the oscilloscope in XY mode, and this way we have control over the vertical axis and the horizontal axis using these two inputs, using the two channels of this oscilloscope. Or we can go really slow like this, or we can go way faster if that's what we need. And in order to know how fast it goes, once again we need to take advantage of the graticules that we have right here, and then we look at our horizontal setting, and this way we can get a feel of how fast the signals are, what's the frequency, what's the period, and so on. Then I will also show you that this scope has some nice tricks so that you don't do the math on your own manually or something like that. So you can see the horizontal divisions right here, and once again the time-based setting, just like for the vertical section, tells you what one division on the horizontal axis means, which in our case is 0.5 something, and then we need to see what the unit is. So for this section of the dial, the unit is milliseconds. If you go really slow, the unit is seconds. We have a small s right here. And for faster settings, the unit here is microseconds. That's because they didn't want to write a whole bunch of zeros here. They are changing the units for different sections of this dial, and as you can see, you have some separators here. So from this separator to this one, the units are seconds. From this separator to the next one, we have milliseconds, and so on. And in case you're wondering how fast this scope can go, well, let's see. Let's adjust the camera just a little bit. As it turns out, it can go to 0.05 microseconds per division. And if you do some quick math, well, 0.5 would be 500 nanoseconds, and 0.05 would be 50 nanoseconds. And if that's not enough, you can enable magnification and you get some extra zoom on the horizontal axis if that's what you need. Anyway, it's not crazy fast by today's standards, but it doesn't really matter for today's discussion, because today I want to demonstrate how it works, and you will see that it's actually pretty fast for some things. We'll do some experiments a little bit later. Okay, so now that we see how we can adjust the time base, by now I think you have a feel of what this does. For example, if the signal looks something like this, then probably the time base is way too slow for you to get any detail, so you need to make it faster, and then you get some more detail. And maybe if you want to look at a particular section, or if you want to see just a period, you make it even faster, and then you only see one period or something like that. Once again, there are no hard rules here. It all depends on what you're trying to get on the display. Okay, with this in mind, let's move on to the other settings that we have here. For example, let's see. Okay, so an interesting thing with these scopes is that they actually have two time bases. So this allows you to do like a zoom on the horizontal axis, and I can demonstrate this really quickly. So this knob is really interesting because you can actually pull it out like this, and then you can rotate this section without this section rotating. So by doing this, the outer knob sets the speed of the secondary time base, which is really interesting. And now we can do this a little bit faster than the primary time base, and at this point nothing happens, and that's because of the setting right here, which is the horizontal display setting. On a scope like this, you have multiple modes for the horizontal display, and this one is your basic mode, which is A lock knobs, as they call it, and this one works just like any other scope. However, things get really interesting once you select any other mode. Let's go into mix, and now we have some weird thing going on. Let's see if we can adjust it. As you can see, now this is not really how it's supposed to look, so something weird is going on here. Let's see if we can adjust it. This is not 100% what I expected. I think we are not triggering the second time base properly. Let's see. Now we don't trigger it at all. Is it breaking down? Is it breaking down in camera or what? This thing used to work, I swear, and now it doesn't really do what it's supposed to do. No, that's strange. So yeah, anyway, what the secondary time base is doing is it can actually zoom in on the horizontal axis, but we get a double trace here or something like that, which is really weird. I don't fully understand why it does this. This is strange. Does it have to do with the settings? Oh, yeah, sorry. Wrong settings on the multimeter. Okay. Now it's doing the right thing. So, as you can see, you can actually sweep at one speed up to a certain point, and then once you trigger the secondary time base, you can change the sweep rate. And now, for this section of the screen, it sweeps at a much larger rate, and this allows you to zoom in on a specific area of your signal. And you can also change the delay between the two time bases using this knob, which produces a really nice effect that some modern scopes don't have actually. For example, my Siglant, I don't think it can do this one. I haven't found a similar functionality, but this one can easily zoom in. So this is really nice. Remember, everything is analog here and everything is real time. So the fact that they managed to zoom in on an analog waveform is absolutely genius in my opinion. And I'm not sure here, but Tektronix could be the first one who managed to pull this off, because it's quite a thing to do something like this, and they managed to do this even with hybrid circuits using vacuum tubes and stuff like that. So they have some really old scopes that are capable of doing this. So yeah, here's how you can zoom in on signals using, I would say, purely analog stuff, purely analog electronics. And if this is not amazing enough, you can do some other things with the secondary time base. For example, you can go into the next mode, which is A intensified, and now it basically intensifies a certain area of your signal so that you can highlight a certain area. This could help maybe if you're taking some captures on film or something like that, because remember, this thing used to have a dedicated film camera that you could attach here, and you could take some captures for your documentation, data sheets and whatnot, because that's how you did things way back when. I'm obviously too young to have seen this in real life, but that's how they rolled. Some of them had Polaroid cameras for instant results, and some had classic film cameras. But anyway, I would say that capturing any sort of waveform would have been a pain. I mean, imagine getting the exposure wrong and you would find out a week later or something like that. It would have been a complete mess. So yeah, we have to appreciate what we have today, because everything is instant in the digital world, right? I mean, the Siglant that I have can be connected to the network, and I can see everything real time in the browser, so that's really convenient. But some time ago things used to be less convenient than this. Anyway, here's how you can intensify a certain area of the screen. However, this is not exactly what I was trying to show right here, because the right side is missing, and I think there is a mode where you can just highlight a certain part of the screen. Maybe if you change the settings, I forgot how to do this. Yeah, something like this. Okay, maybe we have to change this. Okay, and then you also have another mode which is be delayed, and now we are only looking at the secondary time base, I guess, because the rate is much higher. So I think in capturing some events this makes sense, because yeah, I forgot exactly how it works. I think it's still using two time bases one way or another, so I think you have to trigger A time base and then you have to trigger the B time base, and then you actually get a trace or something like that. So yeah, it was really flexible even with purely analog circuitry. So let's see what we can do with something like this. Well, we can actually measure frequency without doing the math like I've shown for the amplitude. So usually with analog scopes you really had to count the divisions in order to see your amplitude and frequency, and this holds true for finding the period unless you have some fancy functionalities like this scope has. Once again, we are at 100 kilohertz, so let's see how to find the frequency manually first of all. Well, we can align one peak of the sine wave with one of the vertical lines, and then we need to see where the other peak occurs, which is two divisions later, and then we have to look at this and multiply by the time base setting. So the time base setting is 5 microseconds per division, and we have two divisions up to the next peak, which gives us 10 microseconds. So that's our period, and then if we do the math, 1 over 10 microseconds gives us 100 kilohertz. So this is one way of doing it, but since this one is a fancy oscilloscope with secondary time base and all that, we can actually use the multimeter, the integrated multimeter here, which is DM44, to do exactly the same thing without us counting divisions. So to do this, if you want to measure the period, then you go to the time setting right here, and then you have to enable the secondary time base and make it much faster than the primary one, and then you go to A intensified, I think, yes, and now you have two areas of the signal that are highlighted, and I can reduce the intensity here so you can see the highlights better. Okay, and as you can see, this one controls one highlight and this one controls both actually. So let's align the first highlight on one of the peaks, probably like so, and then we can use the second knob to align the second highlight on the second peak. And now we can simply read out the period here, which is 10 microseconds. Isn't that amazing? I think it really is. It's a genius thing, once again. Tektronix analog wizardry. So with a feature like this one, with a secondary time base and the digital readout here, you don't really have to count the divisions. You can simply use these highlights and you get the time difference between two different events. So if you align these two peaks on the sine wave, you can actually measure the period. And not only that, but you can actually readjust it to display frequency. So you can use this setting and now it displays frequency instead of period. And as you can see, we have 100 kilohertz. It says right here. So you don't have to count the divisions anymore. So I think this is really nice. And of course, as a side note, we have other ranges here. So this multimeter has two inputs right here, and you can measure voltage, ohms, and temperature. I don't have the temperature problem, fortunately, but in theory it can do all that. And once again, by going to A and lock knobs, we get our average oscilloscope. No secondary time base, just a single time base, and yeah, basic functionality. With this in mind, I think we could go on to the next section of the oscilloscope, which is the trigger section. Well, the trigger section is really interesting, and it's something that actually Tektronix invented way back when on using vacuum tube gear. First of all, it's something that came before of course before digital scopes, before transistor scopes and things like that, because they figured out that not only do you have to run the time base at a certain speed in order to display the signal with respect to time, but you also have to synchronize it with your signal. And if you don't do that, you get a really annoying trace that is almost unusable. So with a good scope and with the right settings, you don't even know that this subsystem is there, but if you screw it up, then you get a really annoying trace. So of course the easiest way to demonstrate this is to screw it up on purpose. That's why we have the trigger source here, and we can trigger to something that doesn't exist, like the second channel. And now the trace looks like garbage. You cannot see what's going on. This happens when the trigger is not adjusted properly. So as you can see, if you get a sweep that is no longer in sync with our signal, the sweep moves so fast across the screen that you don't really see what's going on. And since somebody mentioned the verniers here, yes, you can actually try to synchronize it by hand just to get a feeling of how difficult this is. So let's turn the vernier a little bit and maybe we'll get some detail. See, something's going on as we adjust it. Oh, it's incredibly touchy. I cannot describe in words how touchy it is. It's still not right. Let's try to adjust it some more, and maybe you noticed it. Oh, and here it is. So by adjusting it, we get our trace back, but as you can see, it's going all over the place. So if the time base is just a little bit too slow, it runs one way, and if it's just slightly too fast, it runs the other way. So how on earth can we make this trace stable? Because remember, we are actually not allowed to change the rate, right? Like the speed really has to be the same no matter what. The sweep has to be at a constant speed from left to right regardless of our frequency, because otherwise we lose the calibration and this setting doesn't make any sense. However, we still have to synchronize to our signal. So how on earth can we do that? Well, there is a trick to this, and the trick is hiding in plain sight if you know what to look for. You can see here the word hold off, and the word hold off is really important for this discussion, because what the scope does is that as soon as the sweep comes to an end, you can imagine that you don't really have to start the next sweep right away. You can get a first sweep at a constant rate, then have a break, and then do another trace, and then have a break and do another trace, and so on. And that break between two traces is called a hold off. Now, the interesting thing about the hold off is that the amount of hold off that you have between two traces can actually help you synchronize the time base with your signal that you're trying to observe. And doing it manually is a complete pain. It's almost impossible to get it right. Or actually, let's try. Look, you can adjust the hold off manually, why not? And as you can see, now we're not changing the rate anymore, by the way, which is really important. So we are not using this vernier, we are just changing the hold off, so which is the weight between two sweeps. And as you can see, we can almost get it to sync, but it's very hard, and this adjustment is very touchy, so moving it by a millimeter makes the trace run all over the place. But you get the point, right? So yeah, if only there was a way to do this automatically, right? Well, it is. There is a way to do this, and this is called the trigger circuit of the oscilloscope. What it usually does is that it has some sort of comparator inside, and it compares the input signal against a fixed reference voltage. This is basically what the trigger circuit does, and you can adjust the reference level using this knob, which is the trigger level. So if the trigger level is out of the range of the input signal, then the scope is untriggered, which is indicated by a running trace, and which is also indicated by the trigger light that goes out. So you have to adjust it until you get a stable trace and the trigger light comes on. Of course, this being two-channel oscilloscope, there are multiple trigger sources. So right now we are feeding in a signal into the first channel, so the trigger source has to be channel number 1 in order for this trace to be stable. If we go to channel number 2, of course it's unstable because we have nothing here. And you can change multiple things here. You can change not just the level but also the polarity, and this should in theory change the phase of the signal, but yeah, for some reason this one doesn't make contact properly. Oh, now it works. So depending on what you're trying to get, you can adjust the trigger polarity. As I said, you can adjust the trigger source, and as I said, the scope and most scopes can even be triggered externally by some other signal, and you can select this. You can select external triggering, and then it triggers to whatever you feed into this BNC connector. You can also trigger it onto the line frequency, which is useful for working with line frequency circuits, of course. And you also have a normal mode, which I forgot how it works, but it usually triggers to whatever you have on the display. And then, just like with vertical section of the scope, you also have multiple coupling settings for the trigger section. So you could do AC coupling, you could do DC coupling, and then we have some extra modes for something else. We can have low frequency reject, which, as the name suggests, rejects low frequencies, so it's like a high pass filter. And then we have high frequency reject, which is like a low pass filter. And they both can help when you have some complex signals, and maybe they have some sort of high frequency garbage or something like that that could mess with the trigger circuit. Since everything is analog, it's really useful to have some sort of filtering at the input of the trigger circuits. Not all scopes have them, but Tektronix does, because once again they thought of everything. Okay, let's see what else we should talk about here. Well, the trigger mode is another important setting, and this makes all the difference in certain situations. Right now we are in auto mode, which means that regardless of the trigger circuit, the time base fires anyway. So this means that if we lose the trigger condition for whatever reason, for example, if the trigger is not configured properly, or even if the signal is missing, the time base triggers no matter what, and we get a sweep. Now, of course, we have different modes here because maybe we don't want to do this, and maybe we want to stop the trace in case the trigger condition never occurs. That's why we have the normal mode. With the normal mode, you really have to trigger the scope in order to get a trace, and this happens with this helps actually for some signals that have a weird repetition rate. So let's say something is not really perfectly periodical. Let's say you're looking at something that's relatively random. Well, when your event doesn't happen, you probably don't want a trace, because then you would have a mix on the screen between your actual event and the straight line when nothing happens, and that messes up the display. So if you only want to have a triggered sweep, then you use the normal mode. And as you can see, the trace is out because we are not triggered. So we can trigger it once again by going to DC coupling and by adjusting the trigger level properly. And now, as you can see, once we are triggered, we get a trace. If you lose the trigger, you lose the trace. That's what normal mode means. And then we also have a different mode, which is called single sweep. I think this is pretty self-explanatory, but once again we can slow down the scope a lot and see what happens here. So as you can see, here we have a repeated trace, but we can go to single sweep, and in single sweep we only get a single trace, and this is useful for monitoring singular events. For example, let's say you're trying to look at the startup of a power supply or something like that. Well, you probably only want to trigger the scope once when the startup occurs, and actually what happens here is that when you press single sweep, as you can see, the scope is ready, but it's not triggered. So now it's waiting for your event, and as soon as something triggers the scope, you will generate a trace, and then the time base is off. And this, in conjunction with the storage mode, can actually help you monitor, let's say, singular events or something like this. So you have to use your imagination here. This could be the rising edge of something, the startup of a power supply, or actually the the ramp down of a power supply or something like this. With the storage you can have a more or less persistence image on the CRT, especially if you press the save button. And then you can analyze your trace, and of course this sort of persistence is just natural for digital scopes, and the trigger modes work exactly the same. So yeah, I'm just using this as a teaching aid, but things are pretty similar on the digital scope. And also in some cases the display can get messed up when the trigger event occurs, and maybe you don't want to trigger on every single edge of a signal or something like this, especially if you're looking at a video signal or something like that. And this is where the trigger hold off comes in handy. So you can adjust the hold off manually in some cases, which once again adjusts the break between two sweeps. So if nothing else works, this is worth trying out, and sometimes this makes the display a lot cleaner. So yeah, we are coming to an end on this explanation, so let me know in the comments what you think so far, and if it managed to shine some light onto this topic. Oh yeah, Mad Scientific said that I forgot to mention the z-axis. So he's right, I forgot to mention this. The z-axis is a weird concept at first, because obviously this is a 2D display, so you would wonder where on earth is the third axis on a 2D display. Well, the third axis is the intensity axis, and on this scope you can actually modulate the intensity externally. This is a bit inconvenient to show because I wasn't prepared for this, but this scope has an extra BNC at the back, which is the z-axis modulation, and you can do that to modulate the intensity of the beam, and this would be useful for displaying analog video on a scope. And there are multiple projects and multiple videos about this on YouTube. For example, you can look up a really nice guy from Tektronix. His name is Alan, and he runs a YouTube channel called W2AEW, if I'm not mistaken. This is an amateur radio call sign, W2AEW, and he has a really nice video where he demonstrates z-axis modulation by displaying video onto the screen of a CRT. So there is a dedicated IC for this, which is called a synchro separator. So you can feed that composite video, and it outputs the vertical sync and horizontal sync, which can then be used to trigger some oscillators or time bases for the vertical rate and the horizontal rate, and then you can feed in the time bases onto the X and the Y, and then you can feed the amplified video signal into the Z-axis, and you get a video monitor on your oscilloscope, which is really cool, and it's something that I want to do, but so far I couldn't find the time to do this, but it's on my bucket list and it's going to come, and I want to do this before the chips go fully obsolete, because yeah, the deep version of the chip is already obsolete. You can still buy the SMD part, and I want to get a few before it's too late. I forgot the part number, but yeah, you get the point. It's an LM chip, LM something. So yeah, thank you Med Scientific for this proposal. It's just that I don't have the right setup at this point, so let's leave it like that. It's important to note that this is a feature of most oscilloscopes, and it can be used for multiple things, including turning your scope into a video monitor. And Mad Scientific once again is has an interesting point here. He says, I was never sure what the input was really intended for. I doubt it was for watching TV. Yeah, exactly, but it's all I've seen it do. I have no idea what you're supposed to use it for. No idea, but who knows? Maybe you want to highlight the signals, the certain portions of a signal, so you could use the scope in conjunction with something else, and then if you have like you know, you have an external trigger, so you can synchronize the scope to an external oscillator, and then if you have some sort of delay between that oscillator and the z-axis, you can actually highlight certain portions of the signal. So maybe it makes sense if you use the scope in conjunction with something else, just like the the secondary time base does. So maybe there were such use cases, and once again Tektronix stuff was made as flexible as you could get, because they really wanted these scopes to be able to handle anything within their specs and within their limits, and that's why they have so many features compared to a basic scope. That's why you have adjustable hold off, that's why you have secondary time base, that's why you have storage, because they are really flexible, and in some cases you would want one or a combination of these features. So yeah, we don't have a audience here, we're just 4 people at the time, but yeah, I'm happy to see that we have some action in the chat here, and I'm reading your messages. Once again, good point by Mad Scientific, that it makes sense to have z-axis modulation when you want to use the scope as a vector scope. I forgot about that. So you can blank the beam maybe when you jump between certain points or something like that. Yeah, makes sense. Okay, so let's move on to something that I hope is a little bit more interesting. There are at least 2 things that I want to talk about when it comes to scopes. One of them would be the analog bandwidth of the scope, because I think this is a pretty misunderstood spec of most scopes. And to do this, since you are eager to see the vacuum tube one in action, I think we can fire up the vacuum tube oscilloscope and play with it just a little bit. However, the vacuum tube one is really noisy. So I will do this as an experiment, and unfortunately I don't have a lapel mic. So once I fire up the vacuum tube scope, please let me know if you can still hear me, and if it's too noisy, we will have to use something else. Let's reposition the camera just a bit. Okay, so what should we do first? Some of you were not here right from the start, and if you weren't, I guess you're curious to see what the scope hides inside. So let me give you a quick tour of the chassis, because it's really nice. It's all vacuum tube apart from some semiconductor diodes. Typical Tektronix construction for the 60s. Everything is on ceramic strips. Everything is trying to kill you. Like, there are no reasonable voltages anywhere here. Everything runs from 100 volts or more. This is the high voltage power supply. It produces minus 1.6 kilovolts, and it's all in the open because I had to replace some capacitors here earlier. As you can see, the ones on the right are brand new. It usually has a cover on top of that so you don't kill yourself. And this being Tektronix, of course, it has danger high voltage warnings on all the sections that are high voltage by the by those standards, because if you ask me, everything is high voltage inside, but what's really high voltage is actually labeled, so you pay extra attention to this. But yeah, the times have changed. By today's standards, everything's high voltage inside. Okay, once again, danger high voltage, because in the back we have the two pots for the CRT, the focus and the intensity. And if you know a thing or two about CRTs, you know that these adjustments run at high voltages. So here's the vertical amplifier. It consists of these tubes. Here's the power supply. Of course, it's a tube power supply. It has a neon regulator as a reference. It produces minus 150 volts, and everything is regulated from that. And it has a big ass tube that is the pass element for the 100 volt rail and the 300 volt rail, the 6080 tube. And it has a really interesting delay line which sits between the vertical amplifier and the CRT. And this delay line is literally what they told us in school about coax cable. If you remember it, they said that you can imagine that a transmission line is just series inductance with shunt capacitance, and then you have another series inductance and a shunt capacitor. Well, Tektronix guys took that literally and built the whole thing. And this one delays the signal from the vertical section into the CRT. This is really important because, of course, the time base takes some time to react, and the trigger circuit takes some time to react, and without it, by the time you trigger the time base, the event that you're trying to trigger on is gone. So what you do is you trigger something on the undelayed signal, and then you delay the signal before going into the CRT by like a few tens of nanoseconds, and then you actually get to see your event that triggered the scope, which is really nice because on digital scopes you can have the trigger point whenever you want on the screen. It can be in the middle, it can be right here, it can be right here, and it all works great. And you can see things in the past. Actually, you can see things that happened before the trigger event, but of course on an analog scope everything is real time, so this is pretty much impossible to do, and this is where the delay line comes in. So unfortunately the trigger point is always somewhere to the left of the screen, but using the delay line at least you get to see the event that triggered the scope. And this is something that's also invented by Tektronix, and I don't know of any other scope that used to do this. So this means that other scopes cannot see fast pulses or something like that if they have a low repetition rate. Moving on to the chassis tour, this is the calibrator. This is basically a multi-vibrator, just like the ones that we use for blinking two LEDs. But yeah, this one is based on vacuum tubes, and it outputs the signal here, which once again can go to 100 volts peak to peak. So yeah, unlike a modern calibrator that outputs a few volts or something like this, this one goes all the way up to 100 volts. So yeah. And the top section is the trigger section and the horizontal time base. Everything is of course vacuum tube based. Everything is nice and adjustable, and of course everything is marked on the chassis, so you know what each pot does. And if you're debugging something and you're lost in the circuit, you have the designations and the tube type of every single tube and so on. It's really nice build quality. So let's fire it up. Ready? 3, 2, 1, fire. We have some neon lights inside, which is weird. And some of the neons go out once the scope heats up. I looked at the schematic and I figured out that the neons are actually clamping devices that protect the tubes from an over voltage of the grid to cathode voltage. So they are clamps that clamp the grid to cathode voltage to a reasonable level. And as you can see, it works. It wasn't fully functional when I got it. I had to fix the trigger circuit, and I had to fix the vertical section because it had some ripple, and now we get a perfectly straight line. I also recapped it, and yeah, now we can actually play with it. Please let me know if you can hear me, because I know this is really noisy. Meanwhile, the phone needs to go back to its stand so I can free my hands to do some more experiments for you. And yes, in theory you could trigger a scope using some neons, but in this case this one is triggered by a Schmidt's trigger that is implemented with vacuum tubes. So let's talk about bandwidth for a bit. This scope is a 15 megahertz scope. It has a bandwidth of 15 megahertz, so let's see how this translates into what it can and cannot display, because I think there are many misconceptions about this. Maybe if you come from a programming background or something like that, you would imagine that a 15 megahertz scope works with a 14.99999 sine wave, but as soon as you get to 15 megahertz, then it doesn't work anymore, and I don't know, you get a blank screen or you get an error message or the scope blows up or something like that. I'm not trying to offend anyone, I'm just trying to say that this parameter is misunderstood, and this is definitely not the case. That's not what's going on. So let's see what it actually does. There are at least two consequences of limited bandwidth, and that is you can get an attenuated signal, meaning that you see a lower amplitude than the real amplitude, and you can also get distortion. So let's demonstrate that using the scope that we have here, which is a really limited scope. First of all, let's start with a sine wave. Let's feed a sine wave that is slow enough for this scope to be comfortable with. So we are at 100 kilohertz. We just need to select this input, adjust the sensitivity, adjust the intensity maybe, and then we need to adjust the time base and the trigger in order to get a trace. As you can see, we get a really beautiful trace. So this scope is really usable even though it's very old. It's from the 60s. So to make things easy, let's see what we can do here. Let's go to let's change the sensitivity so that this only spans across one division. Let's adjust the trigger. Okay, and let's see what happens as we increase the frequency. Maybe, I don't know, maybe let's increase the sensitivity and look at it like so. Maybe it's easier to see it this way actually. So at this point we are covering 3 divisions. The signal is no, sorry, we are covering 5 divisions. The sensitivity is 0.2 volts per division, and we are feeding in a 1 volt peak-to-peak signal. Let's see what happens as we increase the frequency. Right now we are at 100 kilohertz. Let's go to 1 megahertz. Okay, this is 1 megahertz, and at this point we only care about the amplitude, and the amplitude is exactly the same, nothing has changed, right? Let's go on to a higher frequency, let's say 5 megahertz. Not much has changed here. We are covering basically the same amount of vertical space. Let's move on to maybe 10 megahertz. And now if you look closely, the signal is slightly smaller on the vertical axis. Let's get closer to that. Okay, how about 12 megahertz? And now the signal is even smaller, right? What about 15 megahertz, which is the bandwidth of the scope? Well, it's even smaller. Remember that initially the signal used to cover 5 divisions, now it's covering 3 point something, less than 4 divisions. So the amplitude starts to drop off. And this is one consequence of having limited bandwidth. So as you go higher in frequency, the amplitude goes lower. We can increase it even more. Let's go to 20 megahertz. And now I think this messes with the trigger circuit and we don't see it properly. Okay, it's back. And now we cover less than 3 divisions, as you can see. We can keep going. 25 megahertz, I don't know, 30 megahertz. At 30 megahertz we only cover like 1 division, even though the amplitude is exactly the same. So as you can see, we are using the scope at a much larger frequency than its bandwidth, and it didn't blow up and it didn't display an error message, okay? So this is not what an analog scope does when we go beyond its bandwidth. However, The true limitation is this one related to amplitude first of all, and we can actually measure the bandwidth of the oscilloscope using this technique. That's because the bandwidth is expressed at minus 3 dB point. So we can calculate minus 3 dB point in a linear amplitude, and it equals to around 0.7 or something like this. So what we can do is we can increase the amplitude until we can increase the frequency until the amplitude drops to like 70% approximately, and that's our minus 3 dB point, and that's the bandwidth of the oscilloscope basically. Let's see if we can do that. So to do this, I think one way to do this is to make this cover the entire screen. So let's go back to a low frequency, let's say 1 megahertz. Okay, I think we can use the vernier for this. And now it covers the entire screen, actually the entire graticules. And now let's do the math for the minus 3 dB point, or around 70%, and that equates to like 21 subdivisions. So as you can see, we have here 6 full divisions, and every division is subdivided into another 5, which means that we have 30 subdivisions from top to bottom. And then as we increase the frequency and we only get 21 subdivisions out of this 30, that's our 3 dB point, and that's our bandwidth. So let's do that. 21 would be, let's see, this is like 5, 10, 15, 20, and 21 would be right here. Let's go. 10 megahertz. We are at what? 28 subdivisions. 12. We are at, let's see, 25, 26. Let's go to 15. 15 we are at 20, 22. So the scope exceeds the specs, as you can see. Let's go to 15.5. Okay, 16 megahertz, still about the same. 18 megahertz. Oh, it dropped a lot. Okay, it's too much. 17. Okay, so this is our 3 dB point, I would say. It's at around 70% of the maximum span, which means that our effective bandwidth is at around 17 megahertz, so it exceeds the official specs. As you can see, we are still at 1 volt peak to peak, 17 megahertz, and the amplitude dropped to like 70%. This is the 3 dB point, minus 3 dB I should say. So this is how you can measure the bandwidth. And if you're still around, please let me know in the chat if you knew about this bandwidth measuring technique. Meanwhile, I will show you another experiment that highlights bandwidth. Let me zoom out. And let's see if the scope can trigger or something on something like this. Let's go back to 15 megahertz. Let's try to properly trigger it and see if we can get any details. So the time base needs to be all the way to the maximum. It usually works better when it's on HF sync for larger frequencies. We need to increase the intensity, and then let's see if we can make it less fuzzy using the stability adjustment. And yes, it's decent, I guess. So now if you want to get even more detail, you can use the times 10 magnification. And now this really looks like a sine wave. So look at this. This is at 15 megahertz, and remember that the bandwidth of the scope is 15 megahertz, so we are using it all the way to the max, and it's still usable, and we still get a relatively sharp trace. So I think this is amazing. However, things are not so good when we have any sort of different waveform. So let's demonstrate that by reducing the frequency, let's say down to 10 megahertz. Okay. And now how about changing the waveform? So let's readjust this, and we have 10 megahertz, 1 volt peak to peak, but now let's configure it to produce a square wave. Now we get a nice square wave here. Let's see how the square wave looks on the scope. Do you want to make any prediction here? How will it look like? Well, we get a beautiful sine wave. Isn't that weird? Okay, let's get rid of the uncalibrated mode, reduce the sensitivity, and as you can see, we get an almost perfect sine wave. So what gives? There is no trickery involved here. This is a square wave. This displays a sine wave, and I would say the most logical thing to do is to ask for a second opinion, right? So let's connect the same signal to a different oscilloscope at the same time to eliminate the possibility that this scope corrupts the signal in any way. And then we will compare them to see what we get. So I already have a T splitter here, so I think it's easier to just move the generator to this. Then we can select this input. We are back to our sine wave, and then we also have the signal here, which can go to our digital scope. Okay, so any guess what the digital will say? Let's readjust this, and you can see that it's a sine wave, right? Even though the signal generator produces a square wave. And now let's ask for the second opinion. Are you ready? Here's the second opinion. So what do you think happens here? Well, what happens here is that due to the limited bandwidth of the vacuum tube oscilloscope, we don't really see the square wave displayed as a square wave. And the reason for that has to do with the Fourier transform. So in around the 17th century, a mathematician called Fourier revolutionized mathematics. That's because Fourier actually demonstrated that any periodic function can be obtained using a sum of sine waves of different frequencies, different amplitudes, and different phase shifts. So you can get any waveform using any periodic waveform using a sum of these sine waves. And if this works in reverse, so if you have any sort of periodic waveform, you can split it into sine waves, and this is what a spectrum analyzer does in real time. So what happens here is that if you split a square wave into its spectral components, a square wave will have lots of harmonics. Those harmonics are integer multiples of the fundamental frequency, and due to the limited bandwidth of the scopes, the harmonics are attenuated by a lot. And if you attenuate the harmonics, guess what you get? Well, you get a fundamental, which is a sine wave. So this is what happens here. Basically, the scope doesn't react to the harmonics of these signals because they are way too high for its bandwidth. So it only displays what it can, which is the fundamental, and this is where this sine wave comes in. So this is applied mathematics in a way. This is Fourier's work in action, I would say. And now that I've demonstrated this, I have one more really interesting experiment for you. Since you're watching this live stream, I'm pretty sure that you are aware that the speed a signal travels through a cable is a finite number. So even though in our average daily life experiences, we look at these signals just like they're traveling instantaneously. So we have the illusion that in the moment we turn on the signal generator, we get a display on the screen because the signal looks like it's traveling infinitely fast from the signal generator to the scope. But if you know a thing or two about how waves propagate and about the finite speed of light, you know that this is not the case, and that the signals need a certain amount of time before they travel from the generator all the way to the scope, right? However, this speed is really fast. It's like 300,000 kilometers per second or something like that, which is hard to even imagine. So it would be really nice if we could see this speed using some sort of experiment, using some test equipment or things like that, because it's something that's way too fast for an average human and for our senses to observe. So we need specialized equipment for that. And believe it or not, we can actually see the speed of light and the speed signals travel to a cable, even using an ancient oscilloscope like this vacuum tube one. This is probably the most interesting experiment for today. So let me show you how to see the propagation delay through a cable like this. There are a few tricks to this. The first trick is that you need to generate a really fast pulse. And this is where this pulsar comes in handy. This generates some fast pulses at a relatively low repetition rate, a few kilohertz or something like that. However, the pulses are really fast. They are like they have like a 300 picosecond rise time or something like that. So they are so fast that you can observe the way they travel through a cable. So let's see how they look on the oscilloscope. In case you're wondering, this circuit was initially designed by the great Jim Williams, and this was redesigned by my friend from Gears and Gear, who also runs the YouTube channel. So to use this, it's better to use a 50 ohm termination. This one came once again from Gears and Gear as a gift. It's a Tektronix 50 ohm termination, and this plugs into the scope. And let's see how those really fast pulses look like. Let's see if the vacuum tube scope is able to see them. To do this, we have to turn the pulsar on. We have to select this input, DC couple it into the scope, disable magnification for a while, and then let's adjust the trigger until we can actually see the pulse. Here it is. And maybe it's even better if we use the DC mode or something, I don't know. We have to tweak the settings a little bit because the pulses are really fast, but eventually we can see them. Okay, AC, is it better? Oh, see, you have to play with it just a little bit because you have multiple adjustments here. So we have to adjust the DC level and also the stability until we get a really nice pulse. So here it is. This is really fast because we are at like let's see, we are at 40 nanoseconds. No, sorry, we are at 200 nanoseconds per division right now, and the pulse is much faster than that. And now we can enable magnification, which magnifies it 5 times, I guess, and then we run at an equivalent rate of 40 nanoseconds per division, which is crazy fast for vacuum tube gear in my opinion, and for such a scope. And here it is. I think this is really beautiful. Look at the pulse. You can clearly see it, and you can clearly see that this is really fast. Like, look at this rise time. It's actually a lot faster than this oscilloscope is capable of displaying, and that's because the rise time is related to the bandwidth. So let's see what we can do with this pulse. What do you think happens if this pulse runs into a cable? So let's change the setup just a little bit. Also, you cannot see the pulse. Sorry for that. Let me adjust the lights. I hope this is better because the trace is very dim. It doesn't go any brighter than this because the signal is too fast for the scope. Okay, so now that we can see the pulse, let's do something really interesting and run it into a cable. Let's see what happens, and I'm waiting for your messages if you know what's going to happen. So what I want to do is to split the signal so that it runs into the scope, but it also runs into a cable. Let's see what happens then. In order to do this, we need to change the setup a little bit. Let's remove the parser from here. Let's move the termination, and yeah, let's run the parser into a cable like so. So there are no tricks here. The parser goes into a cable that has nothing connected on the other end. Okay, we can hang it in there somehow. Okay, so it's just a plain cable. Let's turn the parser on and see what happens. And actually, before doing this, let me know in the chat what you think is going to happen. Any guesses? Yeah, so Med Scientific got it right once again. We should see a reflection. Let's see if that happens. Nothing happened. Okay, well, we have to select the other input first of all. Here it is, and maybe we have to adjust the settings a little bit. Let's see. And we don't really get a reflection now. That's embarrassing. What happens? I think the cable is too short to see a reflection, but don't worry, we can fix this. So let's see if we get more separation if we increase the length. So I will add another section of identical cable. Oh, there we go. Now we really see it. This should have been longer, but anyway. And here it is. Now we get a really distorted pulse. That's because now we can actually see the reflection. So this is the initial pulse, and this is the round trip delay. So what happens here is that the pulse travels into the cable, it reaches the end, and then since this cable is not properly terminated because this is an open circuit, the pulse goes back to the generator, it reflects, and this is the round trip delay. So we can actually estimate it, and it's around what, 30 nanoseconds or something like that. We are at 40 nanoseconds per division. So as you can see, we can actually see the speed of light using this basic equipment here, just a pulsar and a crazy old vacuum tube scope. This is fast enough to see the speed of light. This is not actually the speed of light, but it's actually the speed that the signal travels through the cable. So remember that speed of light is defined in vacuum. However, this is obviously not a vacuum. This is a specific type of transmission line. So for any other medium, the speed of light is actually lower. And whenever you're working with any sort of coax cable, you actually know the speed that a wave travels through it with respect to the speed of light in vacuum. And that speed is usually expressed as a velocity factor. So basically that's a factor that you multiply by the speed of light in order to get the speed of the wave through your cable. And I think the velocity factor is somewhere like 0.7 or something like that. So this is running at 70% of the speed of light or something like that. Okay, so let's do some more tricks here. And I think it would be interesting to short out the cable to see what happens. Let's short it out and have a look at the pulse. Okay, this doesn't work very well, but you can see that the waveform changes. Actually, the reflection is inverted if you short out the pulse. Oh, I wasn't making contact. Wait. Here it is. Now we get an inverted reflection because the cable is shorted. Let's try to readjust things. Oh, here it is. Okay. This is really fuzzy, but you get the point. This is our new reflection, which is inverted because this is shorted out. Okay, so now we are back to our normal reflection. And if you've watched this live stream so far, please let me know how to get rid of this reflection. I'm pretty sure that most of you already know the answer. Meanwhile, I will prepare the demonstration that gets rid of the reflection. So, any comments in the chat? How do we get rid of the second pulse? Yes, that's right. We need a resistor, and this is where things get really interesting because any transmission line has a specific impedance. It's called a characteristic impedance. So in order to get rid of reflections, you need a resistor at the end that is equal to the characteristic impedance of the transmission line. So since this is a 50 ohm transmission line, what we need to do is to add a 50 ohm termination resistor like this one. This is a proper RF termination which has a BNC connector. The phone doesn't want to focus on it, so sorry. It's not that exciting, it's just it looks like a BNC connector, but it has a stub on the end. Okay, and now we can connect it to the cable and let's look at the waveform. And as you can see, the reflection is gone because now the cable is properly terminated into 50 ohms. So once again, this is the proper termination and no termination. Once again, Mad Scientific has a really interesting point here, saying that they're surprised that the scope has very little jitter at this sort of speed. Well, to be honest, I'm amazed too, and yeah, it's really nice that it works as good as it does, but it works as good because I also worked on it a little bit. So there were some tubes in the trigger section that were too weak for it to trigger properly, so the scope was tweaked a little bit before we get into this sort of performance, to be honest. So it wasn't like this when I got it, but now that the circuit is properly adjusted and the tubes are in good shape, it works. But still, I think this is amazing because once again everything is running at full spec here, so the time base is all the way up to its maximum, and we also have 10x magnification, and we still have a stable trace. It's relatively intense. I mean, it lights up enough so you can see what's going on. So yeah, it's quite a thing for something that old. And remember that even with such a limited scope, you can actually do lots of stuff. As you can see, you can actually see the speed that the signal travels into a transmission line. And yeah, maybe we can repeat this on the other Tektronix. What do you think? Let me show you the tubes inside, because now they are lit and they are really beautiful, by the way. So once again, let's do a live tour of the chassis while it's on, because this is where when it's the most beautiful. I love the warm glow of vacuum tubes, and you probably do as well since you're on this live stream. This is the vertical amplifier. The tube that's glowing brighter than the others is the neon regulator. This is providing minus 150 volts, which is a reference voltage for the regulated power supply. Yeah, exactly. So the chassis is not even shielded properly because all the panels are out for you to see what's in here, and it still performs. So amazing engineering. This is the power supply. This is the pass element for the power supply for the 100 volt and 300 volt rails. Of course, it has a fan. It has some neon lights performing all sorts of functions, including clamping on the grid voltages. This is the high voltage power supply, which is a switch mode power supply. Of course, it is powered by some tubes in the back, and here are the high voltage diodes. So yeah, better not touch those because they are running at 1.6 kilovolts as we speak. Here is the horizontal section, and in the back we have the high voltage power supply. This is the high voltage oscillator and the output tube for the oscillator to the left. And this is the multi-vibrator for the calibrator. This puts out a square wave for adjusting the probes. And now, if you want, we can perform the same experiment on the more modern Tektronix. Let's turn this off so we get less noise here. Oh, that's much better. And now let's do the setup here. Let's see what it looks like on a more modern scope. Still old and analog, but definitely newer and faster. And quieter, by the way. That's because in this model the Tektronix guys went through all the trouble to put a speed controller on the fan. So it has a temperature sensor and it has a motor driver that adjusts the speed of the fan. So it's over engineered in the vacuum tube one, it's a basic AC motor that runs at full power all the time. So let's see if we can see the pulse first of all. Now the pulsar is on. We are on DC coupling and we don't see much. Even though the scope claims to be triggered, at this point it's probably too slow for anything to show up. Let's keep increasing the speed of the time base. Oh, and here it is. We have to compensate this with more intensity. This is all the way to the max, and as you can see, this puts this scope out of its comfort zone as well, because it's a really thin pulse. But it's definitely observable. So let's remove the 50 ohm termination once again and see what we get, and see if the reflection is easier to see on this one. Oh, it definitely is. We have even more reflections. Once again, we can measure the round trip delay of this signal, which is probably easier to do if you enable times 10 magnification. So yeah, the signals are slightly easier to see on this scope, because with the times 10 magnification you have a significant distance between them, and you can once again measure the round trip delay. So we are at what, 550 nanoseconds per division without the 10x magnification, and with the 10x magnification we are at an equivalent rate of 5 nanoseconds per division. And let's measure the distance between the two peaks. So 5, 10, 15, 20, 25, 30, so it's 30 something nanoseconds, and on the vacuum tube scope I said that it's around 40, right? So they're pretty close to one another, I would say. We are close enough. So even with the vacuum tube scope we were able to estimate the round trip delay through a cable that is only 2 meter long or something like that. I think this is a 2 meter long with the two sections connected together like I did. So this is what we are looking at. So yeah, that's about it. I really wanted to show you guys some experiments here, and I really wanted to talk about how to use the oscilloscope while also interacting with you. And I have to admit, it was really fun. I didn't know what to expect, because this is my first live on YouTube, so I was really happy that you interacted with me throughout this live stream, because this made it a lot more fun. And of course the plan is to shoot some videos on all of these topics, so please let me know in the chat if you find them interesting and worth demonstrating in dedicated videos, because some of the things from this live stream were demonstrated before. However, some of them are let's say new on this channel. For example, I wanted to do the reflection experiment that we have right now on the scope, and I didn't have time to shoot a video on this, And I also want to demonstrate the bandwidth thing that I've shown you before. However, in case you want to revisit how an oscilloscope works and how to do all these adjustments, for this one I already have a dedicated video, which is quite long, almost an hour long if I remember correctly. So grab some popcorn and watch it if you want to know how to adjust your scope. And it pretty much covers what I've shown in the beginning of this live stream. Unfortunately, I forgot to explain some of the functionalities of this scope in the video, so this live stream has a little bit more information on certain topics than in that video. But if I remember correctly, the video also talks about quantization and sampling, which were not demonstrated today. So I think it's time to wrap it up here. Thank you so much, guys, for watching all this. Thank you for interacting with me, and stay tuned because there will be more videos on this topic and definitely more live streams like this one. And please let me know in the comments what sort of things you would like me to do during a live stream. If you have any other ideas that are related to electronics, I would love to cover them in videos or in a live stream. Hello, Katalin. Fortunately, you're kind of late. We're just wrapping things up here, but the live stream will be available on YouTube. So I'm pretty sure that if you're interested in the experiments that we ran today, you will be able to revisit them. Man Scientific says anything audio equipment works for me. So that's a good suggestion. It's also something that I like. So yeah, I will have to take advantage of a repair, of an ongoing repair or something like that, so that we have some sort of thing to play with. Otherwise it could be a bit boring. So we should get the timing right on this one. Maybe whenever I will be working on an amplifier, that would be the right moment to do something like this live stream on audio stuff. Okay, an interesting question here from Katalin. Do you think about moving to YouTube since TikTok is at the risk of being banned? Well, you know, I don't see it much as an act of moving from one platform to another, because at this point I would like to increase my audience by exposing myself on multiple platforms. Most of the time I go live in Romanian on TikTok because there's where most of my audience is. And you know, since I'm putting the effort into running some experiments, doing some demos live, explaining certain things and whatnot, it's a lot more satisfying for me to maximize the audience. But this doesn't go against going live on other platforms, I guess. So I don't see it as a migration, but you know, my content is almost identical on TikTok or YouTube, I would say. So yeah, unfortunately I don't have a setup yet for going live on multiple platforms at the same time, so I'm considering that as well. but I don't really see it as an act of moving from one platform to another anyway. I would love just to go live on multiple platforms at the same time, maybe experiment with Twitch, even though it's optimized for gaming, so I'm not sure if I will be able to gain any sort of audience there, but I have to, yeah, I want to try Twitch at least once to see where it goes. This is also some sort of experiment because it's my first live on YouTube, as I said. Yeah, maybe I'll do an OBS setup and go live on multiple platforms at the same time. On the other hand, I hope they won't ban TikTok like they did in the US, because that's where I get most of the views, likes, interactions, and so on. And at this point, and on the Romanian account, it started being really nice and interactive. People start asking questions around the various videos that I post, and that's really nice. So on TikTok, it's really convenient to do a video reply and maybe come with an answer to their questions in a video format, and then more people get to see it, like it, interact with it, and so on, and it's more interactive. And at this point, it produces a lot more views than YouTube does. Let's reposition the phone a little bit, because there are some messages in the chat that I would like to address. So yeah, just to understand the setup here, I'm looking at my own live stream on the computer, and I'm reading the chat there because it's a bit more convenient, and for some reason the chat on the phone just disappeared. I don't know what's up with that. I feel like an old man working with technology for the first time. Oh, it's back. I'm not familiar with the interface of the YouTube live, sorry. So Andrea says that TikTok is not good for long videos, plus too much censorship. Yeah, well, they're trying to change things around. For example, now TikTok allows you to upload long format videos, and I have like a tutorial on how to use the oscilloscope or something like that, and it's like 40 minutes or something. It's close to an hour, and I don't know, they let me upload it. So as soon as they lifted the limit from 10 minutes up to an hour or whatever it is today, then of course I uploaded the YouTube videos there, and yeah, people are watching it, but I'm pretty sure they don't have the patience most of the time to watch it until the end. Yeah, Serbian beer, by the way. I went to the Nikola Tesla museum in Belgrade in Serbia, and I also got some local beer, because why not? Not very family friendly content. Yeah, I mean okay. Yeah, and Mad Scientific confirms that TikTok is gone in the US. And you know what, I watched all those videos about Americans complaining about this, and yeah, uh, it's sad, because people worked hard to build communities there, and now they're gone. And I found it really funny that they are migrating to Red Note, which is the Chinese social media app that is approved by the Communist Party and so on, and they're called TikTok refugees. And now it's a wild thing going on there. All those interactions with the Chinese people, and like a clash of cultures, and they're shocked about various things about the different culture and so on. It was really fun, and I was so curious about it that I actually created a Red Note account just to see what's going on, and it's really nice. It's fun. Like, Chinese people are asking Americans to help with their homework, their English homework and whatnot. And then um, yeah, the Chinese guys say that hey, you can stay on this app if you upload photos of your cat. And then the Americans comply, upload photos of their cat, and then the Chinese go, yeah, now you can stay. We approve your stay here. So all sorts of funny things, making fun of an unfortunate situation actually. I'm really curious to see if it will come back to the US, and I hope it does, because I used to watch some American TikTokers. I think there are a few guys who do technical stuff on TikTok as well at the time, who I used to watch. And also Gabriel here said that he has watched my video on troubleshooting using the oscilloscope. So yeah, I really love oscilloscopes, as you can see. So I made multiple videos on this topic, but there are some that are not covered in English, if I remember correctly. So I did one about troubleshooting an audio amplifier using the oscilloscope. Maybe that's what Gabriel is referencing in this message. And at that point, I think I was in a rush and I forgot to shoot it in English too. So I kept I kept saying in multiple occasions in my videos that you need to have a systematic approach when troubleshooting, and when it comes to an audio amplifier, I demonstrated that you can use a signal generator to apply a test signal at the input of the amplifier, so that you have a nice and regular signal, as opposed to running your guitar into it and having an irregular signal that you don't know how it's supposed to look in the first place. And then I demonstrated that you can have a look at various test points throughout the circuit using the oscilloscope to see if your signal is correct or not. And it was really fun to see, because it had an overdrive channel, and you could see which op amps were involved in buffering the signal and which ones were involved in the overdrive channel or the clean signal. And you could switch the amplifier between one channel and another and see how the waveforms changed on the scope. So yeah, maybe this would be nice to see in English as well, so I will consider doing a voiceover or something like that. Yeah, I think it's time to wrap it up here. Thank you anyone for your time. I really hope you enjoyed this live, and stay tuned, because there will be more videos like this and more live streams like this. Thanks anyone for tuning in, and I will see you some other time. Bye.